Class, Mr. Moyden here with a tutorial video covering the mean value theorem. Let's take a look at these two problems. The first one is multiple choice problem. It says, let f be a twice differentiable function. Values of f prime, the derivative of f, at selected values are given in the table above. Which of the following statements must be true? So the first thing I want to notice is the fact that we're given values of f prime, which is to say that these values here are the slope of the function f. I observe that all of these functions' slope values are positive, and that indicates to me that the function appears to be increasing. So at first glance, you might think that choice A is true, but there's a couple things to note here. The word must is a very powerful statement in terms of what we're saying, and also we're only given a snapshot as to f's behavior. We know the slope at -1, 0, 2, 4, and 5 are positive. We don't know the slopes at other places, and for all we know, the function could be decreasing in places in between, so we cannot say that A is true. The graph of f is concave down for that interval is choice B. Just to reiterate what concave down means, a function is concave down when its derivative is decreasing. Another way of saying that is the second derivative is negative. Now, once again, looking at the f prime values here, they do certainly decrease. 11 drops to 9, drops to 8, drops to 5, drops to 2. But once again, we don't know if f prime isn't, let's say, 12 or 20, somewhere in between -1, 0, 2, 4, and 5. Again, we have a limited view here. So we cannot determinatively say that the graph is concave down because we can't say f prime is necessarily decreasing the entire time. Certainly it appears to, but we don't know for sure. There exists some c, and as soon as I see that, I'm reminded of either the mean or the intermediate value theorem. There exists some c such that f prime of c is equal to -3/2. Well, kind of going in the opposite direction, if I assume temporarily that these are the values of f prime and f prime's behavior is sort of suggested by these values and nothing crazy is happening in between, to drop from 11 to 9 to 8 to 5 to 2 doesn't mean I pass through -1.5. In fact, I don't seem to pass through any negative number at all, again, assuming that the behavior is sort of indicative of what we're seeing here. And if we kind of assume that things are relatively normal, there's no reason to pass through -1.5, so it certainly need not necessarily be true. Which makes choice D the answer, but let's kind of come up with a determinative positive reason as to why it's the answer, not just by elimination. The first thing I'll notice is that the question's answer, or rather the answer choice here, mentions f double prime. The values, meanwhile, are of f prime. And when we're told that a function's slope has some c existing that satisfies that slope such that we have a fraction, especially like that, equal to it, the first thing I'm reminded of is the mean value theorem. The mean value theorem states that you will find some c in between a and b for which this fraction is true. Now, this fraction, or rather this statement, this equation can be true for a whole host of statements and functions. For example, as long as the function is differentiable, the function whose average rate we're finding could well be f prime. And if so, the f prime's derivative could be satisfied by some c. And in fact, this is exactly what we're doing in this problem. If we let a equal -1, and if we let b equal 5, as it indicates in the interval there, then this would say f prime of 5 minus f prime of 1 over 5, of -1, over 5 minus -1. My denominator is 6, and looking at my tables of f prime values, which for the sake of argument is our function's values, I would have a 2 minus a -11. 2 minus -11 is, 2 minus 11, excuse me. 2 minus 11 is -9, over 6 is -3/2. So this chain of reasoning leads us to the fact that f double prime of c must equal -3/2. Well, sure enough, that is exactly what choice D is saying. This is true provided, provided our function f prime is differentiable, the mean value theorem will hold true. If f is twice differentiable, then certainly f prime is differentiable, and thus the answer must be D. Another table question, this time giving us velocity values at certain times and acceleration values at certain times, or one might imagine f prime values at certain times and f double prime values at certain times, provided that f in this case would be position. The second derivative of position is known as acceleration, and the first derivative of position is known as velocity. So a car travels on a straight track. During the time interval, the velocity is measured, and so on, kind of skipping over the top part of the problem stem. We're told that velocity and acceleration are both continuous. Notice the word differentiable is not used there. We're going to have to make an inference in just a moment. For time between 0 and 60, must there be a time when the acceleration is 0? Well, if I'm looking at the acceleration row right here, the first thing I'll notice is that I go from 1 to 5 to 2 to 1 to 2 to 4 to 2. At first glance, it doesn't appear like I go through 0 because all these numbers are positive and they never dip into the negative region. But that might not be a full picture because, once again, we only have a limited snapshot of certain time values. We don't know what's happening at all times. Now, we also have these velocity values, and we'll note that the derivative of velocity is acceleration. So if our average rate of change of the velocity, by which I mean this fraction right here, if the average rate of change of the velocity is equal to 0 somehow, then by the mean value theorem, you will find some value of c, or I'll just say t here to make it like the problem, for which this fraction is true in between your a and your b. So this is going to be true if the mean value theorem applies, and again, provided that this fraction is equal to 0. So that's what it's asking us. Is this going to be true? Well, the mean value theorem needs to apply. When does the mean value theorem apply? The mean value theorem applies for differentiable functions. Well, we're told that the velocity is continuous. We're also told that the acceleration is continuous. Another way to express acceleration is the derivative of velocity. So if a function and its derivative are both continuous, that would imply that the original function, in this case velocity, is differentiable. And if the function is differentiable, well, the mean value theorem does apply. And if the mean value theorem applies, then we can apply this chain of reasoning that the average rate of change must equal the instantaneous rate of change. In this case, we're wanting that average rate to equal 0. Well, this fraction is equal to 0 when the numerator is equal to 0. That then implies that the velocity at some time is equal to the velocity at some other time. Long story short, we're looking for a repeat of values in our velocity row. And sure enough, there it is. The velocity was negative 20 at the beginning. It was negative 20 again at time 25. And therefore, somewhere in between 0 and 25, there must have been an instantaneous rate of change of velocity, also known as acceleration, that was equal to 0 because the average rate of the velocity, rate of change of the velocity was equal to 0 over that interval. So a typed out answer might look something like this. If I can get this to work, let's see. Yes, it's a yes or no question. MVT applies because V and A continuous implies V is differentiable. I know you can't see that. Let me scroll up. And that's not resizing. All right, well, chaotic looking video. It's all right. New text box for some reason because the software just doesn't want to keep up. Okay. Average rate of change of velocity on the interval 0 to 25 is 0. Therefore, the change in the velocity equals 0 for some time t in the interval 0 to 25. Another way of expressing v prime, of course, is a, so hence a of t equals 0. And if a time would satisfy this between 0 and 25, well, then certainly it'll satisfy it between 0 and 60. And there we go. Sorry, the screen looks as chaotic and crazy as it does, but the software is not cooperating. All right, hope this helps.